But yeah, I'm actually also going to do a quiz. We can take a short break. After that, you can get water or whatever, and then we'll get into the workshop questions. But the workshop questions will take some time, so I'll try to keep this section fairly brief each week. But yeah, so let me know if you want to scroll back up to the QR code here. But this should link to my notes so that you can follow along if I scroll too quickly or anything like that. First thing to note is for your assessments, it's kind of stacked in week 7, so keep that in mind, please. On the Monday, that's when your assignment's due, both part A and B. If you're not already familiar with that, you should be forming groups of 4 to 5 people to do this assignment with. It doesn't have to be people in this class, it can be any class. So it could be like another tutor's class, people from there. But yeah, Kurt said minimum 4 people, max 5 people, and you sign up on Moodle. Part A of the assignment, actually I'll run through it later, but yeah, it's just due in week 7, so keep that in mind. The Tuesday is when your quiz is, so it's kind of stacked. You'll have your assignment due, then your quiz, but it's fine because you're just going to be in the geology headspace because in the second half of this trimester, it's going to switch gears instantly, and we're going to go into geotech design, which is essentially soil mechanics part 2. Don't worry if you're still scarred from soil mechanics. It's easier than that just because it's less content, right? But it's building on from soil mechanics. That's why it's a prereq for this course. Yeah, does anyone have questions about this so far? Or? Okay, so I'll move on. I've got like an overview of this course in terms of what you can expect for weekly content. So yeah, again, the course is broken up into geology and applied geotech. These 5 weeks, they've kind of structured it a bit strangely in my opinion, because we'll be jumping back and forth between a few things. You'll notice in the workshop that we'll do later today that you'll be talking about soils a little bit, but again, that's why it's a prereq for this course. Like, it's a little bit of assuming knowledge of your understanding of soils, but that's okay. And they try to jump straight into stuff like structural geology as soon as possible, because that's what you're going to need for part B of your assignment. But yeah, anyway, you get the idea. They structured it the way they did because it's the best way they've found for the assessments. And yeah, and then the second half is the soil mechanics part 2, basically. Anyone have questions? In terms of like the course outcomes, you kind of want 3 different things out of this course. The first is your technical skills, so your midterm will very much be focused on that. It's focusing on like being able to draw like a geological profile for whatever terrain that they throw at you, and just understanding how like the various rocks and stuff work, and like structures, like structural geology works in an area. So that's kind of why I've put a quiz in this workshop, even though I think most students wouldn't have put a quiz in this workshop. It's because it's going to be useful for your midterm, basically, so that you have some understanding of what the midterm might throw at you, right? And then yeah, the finals is purely the second half of the course. So the finals is just going to be your applied geotech, and that's just all calcs. The first half of the course, nearly no, like it's almost no calcs at all. Yeah, and so assignment part A and B are a bit different. Part A is like research. So you're basically going to be picking an area in the world that you're not going to go to. Like I picked Iceland or something back when I did this course, and you're just going to research like the various interesting geology and geographical features of that area. So I did like some national theme park in Iceland that had like a lot of basalt or whatever. And yeah. And then part B of your assignment, which you're going to be doing in the same group, by the way, that's like site investigation. You go off and you find things like you go to Coogee Beach or Bronte Beach, or like you go to a beach altogether. You want to be like well prepared for that to investigate. You want to like prep the theory, like you want to know what defects are, you want to know what like all the structural geology is and stuff before you go on your site investigation, so you don't have to go twice, for example. It'll save you a lot of time. So you kind of want to know as much as possible going into that site investigation, and you do a big write-up on that. Right, that's the idea. Yep. Any questions? Or is that okay? All right. Cool. So in your lecture notes or in your lecture, Kurt might have talked about geological time. That's the first and last time you're going to hear about that, basically. So the only things to note that you should kind of be aware of is that MA in this graph or another graph that you find stands for mega annum, and Ka stands for kilo annum, right? That's pretty much it. And these are based on like fossils or something. I don't really know, but like, yeah. The idea, the main takeaway from this is that older rock belongs at the bottom, newer rock is at the top, right? And so you can break it up based on that. Yeah, come in, take a seat. Okay. With rocks and minerals, right? So this is from some book on engineering geology that I found. This is essentially the typical rock cycle that you're going to find. They don't dive into this until next week, but I think it's good to give you guys some sort of overview because I think this is the best point to start in terms of teaching the course, right? So you might remember from your year 10 geology, sedimentary rocks, metamorphic, igneous, and they have various properties which I've included here. Rocks and minerals are different things. Basically, you have a bunch of minerals, such as, I've listed a couple here, such as quartz, such as feldspar. You'll hear a couple of other names of the minerals. Those are just components of rocks, basically, right? So sandstone, for example, is a sedimentary rock, and it has a high quantity, it has a high percentage of quartz in it, right? Quartz sandstone. So that's an example. Yeah, it's like a mixture of minerals. That's the basic definition of what a rock is. I want to draw your attention as well to your major types in terms of, you'll hear these names come up a lot. So sandstone, as I mentioned, is a sedimentary rock made up of quartz sand that's been compressed and turned into rock over time. Limestone is what you might find at the beach. It's from the shells of sea creatures. And they also use lime in cement. They use lime to make cement, they heat it up really to high temperatures and stuff. Anyway, you'll learn that in concrete if you haven't done that already. Shale is basically your clay / siltstone, right? So instead of sand particles, it's made up of a combination of clay and silt particles. Metamorphic rock, your schist and shale, those are different metamorphic grades of shale, basically. So it goes, start with your shale, which is your sedimentary, essentially mudstone, right? And that's the parent rock to schist, which has become metamorphosized, and then that becomes, it's the other way around, slate to schist. There's further grades. I think it goes there's one called gneiss or something. But this is essentially degree of metamorphism in your rocks. So there's a couple names for that one, for example. And then lastly, you have your igneous rocks, such as granite and basalt, right? We'll get into that later, but yeah, you should familiarize yourself with a couple of these rock names. They'll come up a lot in the next few weeks. So again, this is a typical rock cycle, because I'm going to tell you the general rock cycle later, but typically it goes something like this. You start with soil. It gets deposited due to various processes, such as alluvial processes, is where a river washes the soils downstream or whatever, and then it compacts, such as that. Lithification is where your soil gets compacted into sedimentary rock, such as sandstone. And then it can get metamorphosized. So the example I gave was shale to slate or whatever, but another example. So sandstone can get metamorphosized as well. That one goes to quartzite. So that's a metamorphic version of sandstone. There's a bunch of these to remember. A lot of the first half of this course is rote memory. But yeah. Um, yep, and then basically when your metamorphic rock or whatever type of rock melts due to like volcanic intrusions from the core of the Earth, it becomes igneous rock once it cools down, and then that can get weathered and start the cycle again. That's the general idea, right? So I want to draw your attention to Earth movements because this is the start of probably the content that you've actually been taught in this course, right? Plate tectonics, right? Actually, sorry, let me jump back for a second. For your general rock cycle, it might look like something like this. It's basically just a more in-depth version of what I had before. The reason is that a lot of these processes are quite rare. So, for example, igneous rocks being metamorphosized is actually quite rare. I think, for example, basalt is an igneous rock, right? It can get metamorphosized into like, you have to Google it, it's like green slate or something. There's like some really rare name for it, but it's an incredibly uncommon process. So that's why I've included the typical rock cycle instead above. But yeah, sorry. So, Earth movements, right? I'll just show you down here. So, essentially the largest scale that you're gonna have to deal with in this course is the entire Earth, right? And specifically, dig into the layers of the Earth and highlight here. You've got your lithosphere, which is basically the crust. That goes into the mantle, which is deeper, and then in the core, right? And there's all these sub-layers which you can refer to, but these are the general 3 terms that you'll be using, right? So essentially in your mantle, you're familiar with the idea of convection. So that's like cycling of hot and cold air, right? So that's these arrows here. So these are convection currents, and they drive like the plate tectonic movement, basically, underneath the Earth, right? And you've probably seen tectonic plates back in year 10 science or whatever for geology, but there's a bunch of different plates. Yeah, we're on the Australian plate. A big name that you might remember is Ring of Fire, which is somewhere around here, around the Pacific plate. So it's your Ring of Fire, that's where a lot of your volcanoes and seismic activity happens on Earth. But the idea is that essentially a plate is the area here, right, that I've highlighted, essentially. Whereas your boundaries for your plates are the outline, right? That's pretty much all you need to know for this. So now we're going into the various types, right? I've included a lot of information here, so it might take a second to digest, but essentially your continental plates, so those are plates with land, right? They're lighter in general, and they contain a lot of felsic minerals that's lacking in iron and magnesium. That causes a lighter color for those types of rocks. Whereas your oceanic plates are heavier, they have mafic minerals, which is the type of minerals which cause darker colors in the rocks. Yeah, we include some examples here. In terms of your boundaries, right, it's how the plates like interact with each other, right? So there's 3 types of boundaries: convergent, divergent, and conservative / transform boundaries. Essentially, from like your engineering mechanics or like your physics point of view, this is your axial pressure, right? This is your axial tension, and this is the shear, right? So plates shearing past each other like that. I'll explain a bit more about that later. I'm going to scroll past this, but if you guys need the QR code, just quickly scan it here. There's a copy of my notes, so if you missed this, yeah, anyway. Because I'll show you more specific examples. Sorry, I'm rushing through this a little bit so you have more time for your actual workshop, but yeah. So yeah, here's what I was talking about. So that's where the plates are being pulled apart, right? Your divergent boundaries like that. Convergent is where they're being pushed together. Transform, the shearing against each other like that, right? Bang. And here they've pointed to specific interactions that happen between like either oceanic plates, continental plates, but I'll just show you below first, right? So with the divergent boundaries, you can have continental plate divergent boundaries. So that's two pieces of land, right, that are splitting apart. It creates something called a rift, right? So that's where there's just a huge crack in the ground, essentially, right? Let's go. Oceanic plate to oceanic plate interactions. Same thing's happening, but there's like a big body of water underneath, right? And yeah, as it's being pulled apart, magma shoots up and turns into more rock because it's being cooled down due to like the water and stuff, right? So that's a ridge. So I'll show you what that looks like on this picture, right? So yeah, in this diagram, they've included the visualization for a ridge, but you can also look these up online for if you want more detail on the pictures. Convergent boundaries. Is anyone doing steels this time?
Steels?
Yeah, steels.
Yeah, I think they're all doing steels.
Maybe not everyone, but like I guess like if you're third year, a lot of you guys are doing steels alongside this. Have you reached compression yet?
Just into the axis stuff.
Yeah. I brought a sponge, right, for this demonstration. So essentially, pretend this is a steel beam. Okay. So forget about geotech for a second. This is a steel beam, and if I'm giving compression, it means I'm pushing it together, right? And then it does this. This is called buckling, right? So if this is sufficiently longer than this axis, it's going to buckle like that. For a convergent boundary, essentially buckling, like the buckling effects of the plates is what causes mountains to form, right? So it's just the earth trying to push up like that. Yeah, so keep that in mind. It's one way to remember it. That's the way I like to think about it because, I don't know, I specialize in structures, so just think of everything like structure, right? But yeah, hopefully that makes sense. For two oceanic plates being pushed together, right? I might draw a diagram for this. Does anyone else need to copy this down? So basically, you have your water, right? And then these are your two plate boundaries, and they want to push together, right? So unlike before, where it had just air that was pushing against it when it was buckling, like that, now we have this water pressure from the water, which is keeping it down as well. So when it tries to buckle, it doesn't create mountains, generally, it doesn't create mountains under the ocean. What happens is this literally just gets destroyed, particles like fly everywhere. And essentially nothing of any geological significance happens here, like no new types of rocks or anything form. Rock just gets destroyed during this process, right? And lastly, this is the most complicated interaction, but it's also one of the most common, and they bring it up in like the midterms and stuff. It's where a continental plate and an oceanic plate converge. Okay. Yeah, and as I mentioned before, the oceanic plate's the one that's heavier. So every single time, that's the one that gets subducted. So subducted means that it falls under. Actually, I've seen this picture before. So this is the oceanic plate getting subducted, right? When it gets subducted, it gets pushed closer to the core of the Earth, right? Which means, and also just think about this, right? The closer you are to the middle of the Earth, does it get colder or hotter? It's hotter, right? So this plate starts to melt, okay? And then that that extra debris that like melts, basically it shoots up and turns into, well, it buckles as well, like before, generally forming a mountain range first. But what tends to happen is volcanoes form very often in this case because the melting of the oceanic plate, essentially, right? And then it shoots up, becomes a volcano. You can learn more about this later, but the type of volcano that this becomes is called a stratovolcano. There's a shield volcano as well, but you don't have to worry about that yet. It's really only something you worry about if you're specifically doing your like assignment research project on it. you don't have, like, volcanoes aren't like a stable part of the course. But yeah, that's essentially what happens. And then with the conservative boundary, right, this is where you have your two plates shearing against each other. But what often happens is these are very like uneven surfaces. So there's a lot of material that gets caught as it's trying to shear. There's a lot of like potential energy or whatever. And then when the material breaks off, causes a large vibration, which causes earthquakes, basically. So you'll see this happening around the Ring of Fire, for example. Yeah. So transform boundary, that's potentially what causes earthquakes, right? Yeah. Does anyone have questions? Is that okay? All right. You can take a screenshot of this, or again, you can refer to my notes. I've just like done a little bit of a pattern recognition for you. It's like all your practice papers with the solutions and the content, like which week's content your midterm's going to be on, right? So all I've talked about so far essentially is week 1, plate tectonics, and it comes up every now and then. So like all in all, it's not like a huge part of the course, but it's good to know because it's mainly for context, right? The rest of the course will get more specific. It's like smaller scope basically. You're analyzing a specific area or whatever, rather than like an entire continental boundary or yeah. Anyway, cool. So what I'm gonna do is I'm gonna quiz you, and then we'll get into the actual workshop. Yeah. Make sure the shuffle questions is off. All right. So if you just whip out your phone, this requires a QR code, and yeah, I'm not kidding. The midterm is literally, I've made the questions a bit easier because it's week 1, but like the midterm is literally just a bunch of either multi-choice or like qualitative questions. There's 0 calcs essentially. So it's going to be stuff like this. Is anyone still joining? Okay. I'm going to close this. All right, everyone ready? Yeah. let's quickly talk about these. So essentially, yeah, sandstone's the right answer for sedimentary rock. Quartz is your mineral, remember? Quartzite is the metamorphosized version of sandstone, and sand is your soil, right? So you want to distinguish these words, right? Shale is your sedimentary rock. It's made up of clay and silt particles, which is your soils, and slate is your metamorphosized version of shale, right? The reason I ask these questions is because you got to be pretty familiar with this for the workshop, because we're going to be working with sedimentary rocks and particles. Yeah, so the Himalayas is like a mountain range, right? That's your continental to continental plate boundary interaction, right? Remember the buckling thing to create the mountains. Mid-ocean ridge would be a divergent example, but underwater, right? Shield volcanoes actually occur, they can occur in like the middle of plate boundaries, right? So like, this is the Pacific plate, right? Ring of Fire, all that. Somewhere like in the middle is Hawaii, right? And Hawaii is actually made up of kind of like old volcanoes, right? And that's the shield volcanoes because they're from hotspots rather than due to plate boundary interaction. Right? So like hotspots of magma can rise up and become a shield volcano.
I don't know the hotspot form.
I don't know. I didn't research past that, but you can look it up if you're interested. Yeah, like especially for your research assignment, part A. If you're interested in Hawaii or something, that can be the spot you pick. Yeah. And Bermuda Triangle is just something else. Okay, so yeah, when your oceanic plate converges with continental plate, what happens is the oceanic plate is subducted, right? That happens 100% of the time, right? This second case is when you have the continental plate to continental plate interaction. This third one is, this is kind of bullshit. This fourth one is the shearing one. So yeah, just different plate interactions. Serena, can you take a photo? Oh, wait. Or you take a video or something. So I'll just scroll through these slowly. Good job, everyone, with your drawings. Wow, thank you. All right, awesome. So now we'll move on to the workshop. So I'll come around and check. I'll check your task 1 pre-homework if you haven't already shown it to me. But otherwise, I'm actually just going to dive you straight into it. And the idea is you talk to the people on your table and solve it together. That's, yeah. And I'll give you like hints as you go, but like, yeah, just put your hand up if you're stuck or whatever. Yeah, anyway, feel free to talk between yourselves.